Welcome back. In these next few slides, we'll study a difference equation. And from this difference equation, we'll study the relationship between it as well as to its block diagram, transfer function, and impulse response respectively. From the difference equation, we can actually generate through a simulation or by writing software code and letting xn be the impulse, and then generate the output as we have done previously. So writing software code, giving x of 0 equals to 1, x of 1 equals to 0, x of 2 equals to 0, and so forth. Simulating the impulse and substituting into this difference equation, we can get h of n, the impulse response. However, we have seen that another way to get the impulse response is through Z transform. Simply by performing the Z transform on y of n and x of n such that we get the ratio of yz over x of z, which is the transfer function. This h of z is the transfer function in the z domain. We know that h of z actually is h of n in the z domain. So if we have h of z, to get h of n, we just perform inverse Z transform. If we have h of n, to get h of z, we just perform Z transform. So h of z can be gotten from h of n or from the difference equation. So you need to move around these three blocks very familiarly. Now, once you have h of z, the other thing we often ask is whether the system is stable or not. So when the system is stable or not, make this into positive powers of z's and factorize it so that it will look into this form. When it look into this form, we can then see where the poles and zeros are. The zeros are those values of z that makes the numerator equals to 0. The poles are values of z that makes the factors 0, such that numerator over 0 is infinity. And in other words, the poles are the roots of the denominator. The zeros are the roots of the numerator. Well, once we have that, we can plot the pole and zero diagram. In this example, because the causal system will find the furthest pole from the origin. In this example, there's only one pole. We draw a little circle around it to say that anything outside this, which is this red lines here, are the region of convergence. And in this particular case, we are interested to see whether region of convergence include the unit circle or not. And yes, it does, and therefore the system is Peeble stable. Now, in the next stack of slides, where we go into discrete time Fourier transform, you'll realize that once we are given h of z, we can substitute z equals to j omega and change h of z into h of ej omega, implying that we are evaluating the transfer function on e of j omega. What is e of j omega? It is 1 e j omega. Omega equals to from 0 to 2 pi. 1 is the radius 1, which is the unit circle. So simply when we are doing that, h of z, where z equals to 1 e j omega, we are evaluating the transfer function on the unit circle. This is a very special place, the unit circle, because h of z on the unit circle is the frequency response for different ej omega. Okay, a complex exponential that is rotating at omega, that is not growing or decaying. It is 1 ej omega. Now, to reach h ej omega, we could have come from h of z by substituting z equals to ej omega. We could have come from h of n because the Fourier transform, so that's in the next slide, in the next part, the Fourier transform of hn is h ej omega, the discrete time Fourier transform. As a relationship between h ej omega and the pole and zero, because actually from the pole location and the zero location, you can actually very quickly estimate the frequency response. We'll go through it with some examples. And lastly, in the previous few slides, we have gone from the difference equation into the block diagram. All we need to do is to follow this block diagram and realize it as df1, direct form 1. So we have xn here, so it's xn. We have xn minus 1 here, so it goes through one delay. This is xn minus 1. Since both of them are multiplied by 1, then here instead of using a triangle, I use a cross. 1 multiply to represent this 1 and this 1. Plus 1/3 yn minus 1. Well, it goes out to yn. Yn needs to be delayed by 1 sample so that we can get yn minus 1 here. Multiply by 1/3. So it's plus 1/3, so it's times 1/3 and go back up again. Okay, so this is the df1 representation of this difference equation. With that, this diagram here shows the relationships between all that we have done except this part, which will be taken care of in discrete time Fourier transform slides. The details of the workings are here, so I leave it to you to read all this. This is a very simple difference equation. It has only one pole and one zero. Alright, just work out through this and you will see how it is done. The only thing that might be difficult is to realize h of n. H of n is realized by the inverse Z transform here. With that, we have concluded our lectures for the Z transform. Thank you.